All right, so this is again for worksheet 12.3. We'll call this part 2. So basically, it's nothing new, just review material. Give you another example of everything, and talk about how all this works. So first off, let's look at lines intersecting in the space here. So first off, when you have, let's say, two lines that are parallel, you might think, okay, you can just look at the slope and say, well, if all the slopes here are 2, 2, 2, and the slope here is 2, 2, 2, that you're done. But technically, you need to still go ahead and solve, because what you could do is have this scenario. So here's one here, but then the other one could have the same slope. They're just behind each other. So you still have to go through. So what would happen if you do your two equations, two unknowns, you'll get like 0 equals 0, which means they're the exact same equation. Where over here you might get 0 equals 4 or something. Okay? So you still have to go through and solve that solution. The other part too is if you have skew lines. So like, for example, you have this and you go through and you have your second one, and therefore they cross at some point. Well, the other scenario would be, okay, you have this, but like, think of two planes, one at elevation at 10,000, another plane at 20,000, and they're flying like this. So they're going to overpass each other, but they're not going to be in the same location. So this would be at elevation at, say, 10,000 feet. This plane is at 20,000. Yes, they're going to fly over on top of each other, but they're not going to collide or anything like that. Okay? So you still have to go through, and in order to do this, you got sometimes here, if you have your x and y, well, you have to use your z to check. So here you could get an xy value, but your z will fail, okay, or some other combination. So your x and z could work, but your y could fail. So you have to go through and check all three values to see what's going to happen. Okay, so let's do one more example here of the math. So you have, let's say R1, so that would be T1, and let's say our starting point is 2, 1, 1 plus T, and let's say negative 4, 0, 1, and our second equation, R2, so we'll call this T2, and we have negative 2, 1, 2, and therefore this is time 2, and our slope is 2, 1, negative 2. Now again, like I said, you want to maybe do a quick check and look at your slope. So if you take 2, 1, negative 2, you can see that they're not the same right off the bat. So let's go ahead and let's start off with our x component. So we have 2 minus 4t, and that's t1, and then we have negative 2 plus 2t, 2. Okay, and let's get our y component, and that would be, I'll use a different color here, so 1 plus 0t1, and our y component for the other one would be 1 plus 1t2. Okay. All right. So it looks like right off the bat makes it easy here. This goes away. Looks like T2 is 0. So I don't have to do two equations, two unknowns. So coming over here, looks like we have 4 minus 4t1. I moved that over, by the way. And since this is 0 here, that would be 0. I guess I moved in the wrong direction there. So we have 4t1 equals 4. t1 is 1. So that's our 2 times. But I still have to check, okay, to see what kind of, for example, what kind of scenario I might have here. Because I have those 2 that could still happen. So looking at my z component, so my z component would be 1 plus 1t1, and then 2 plus negative 2t2. And let's just plug my times in here. So I have 1 plus 1, and 2 plus 0. I get 2 equals 2. So that it checks. Okay, so what does that mean? Well, that means that they actually intersect, okay, at some location. So where is that location? Well, plug in, and let's just, I'll just use T1 here. I could use either one. So if I plug in for R1, and you can check my work here, you should get negative 2, 1, 2 by plugging in there. Now if I do R2, which would be 0 time, that would probably be the easiest one. That would be negative 2, 1, 2. If time is 0. That would be the easiest, because that way just cross that off and you got your point. But if you plug that in up here, actually there, you should get the same value. Okay? So they will be at this location, but 2 different times. Okay? All right. So hopefully that helps out a little bit. Now let's go on to the last new stuff. I'm sure there's a few questions on that yet. All right. So basically, let's project. Let's see, what do I do? A onto B. So vector A onto B. Okay, and this is the same thing as decomposition. So if I say decompositions, okay, realize that you have the component A, where you have A parallel plus A perpendicular. So basically you have your 2 different components of A. All right, so that would mean then that B is our new positive x-axis. Okay, so let's do an example here. So let's say we have A, and you have 5, 1, negative 3. B, 4, 4, 2. Okay, so that would mean that B has to be my new unit vector. Okay, so how to create that as a unit vector? Well, you have to find the magnitude of that. So that would be the square root of 16 plus 4. And I do believe that turns out to be 36 for 6. So therefore my unit vector, so E of B, is 1/6 4, 4, 2. Okay. Now I should have done an example. I'll come back to it later. Another one in terms of basic things, in terms of your process of what to do next here. So the next thing here, what was your step 1? Is step 2 is then multiply your unit vector by your A. So we're going to go vector A, dot it with my unit vector B. So I have 1/6. So you have 4, 4, 2. Dot it with 5, 1, negative 3. And remember, when you do a dot product, you get a scalar. So that's going to be a magnitude that we'll get. So we have 1/6 So we have 20 plus 4 minus 6. So that gives us 18 over 6 for 3. Now we're looking for the components. So here's the part that people always trouble with the third step. What do you multiply it by? Well, you multiply it by the unit vector. And therefore my unit vector, okay, so now I have A dot EB. Okay, if I take this 3 and multiply it by 1/6 of 442, and obviously I'm going to get a half here. So what's this going to equal to? Throw 3 6 or 1/2. 442. That would mean then I have 2 2 1. Okay. Now what is that? Well, that I have found is my A parallel, or my x component of A. Okay, so that's my x component of A on to B. Okay, so you think about it. Okay, here's B. Okay, here's A. So if I draw a triangle here, this is my x component that I found. Okay, and that is why they call it A parallel, because it parallels this vector here. Okay, so what I need now is my A perpendicular. Okay, so therefore, if I have my component of A, which is, so what am I doing here? I have A parallel plus A perpendicular, my decomposition. A is 5, 1, negative 3. My A parallel I just found is 2, 2, 1. And I want to find A perpendicular. So basically I'm just subtracting. So therefore my A perpendicular would be 3, negative 1, and negative 4. And what does that mean? Well, that is my y component of my A, my B. So that is this piece here, according to B. All right, so hopefully that one helps out, another example of that. All right, one last thing I just want to talk about, relating it to some other things here that you might see, especially like in physics. And so let's do this as a scenario. Let's say find the force on a frictionless incline. All right, so let me move that up. So what we have here, we have an object on an incline, and let's say this is 100 kilograms. That's my mass. And let's say this is 30 degrees. So there's different things that they will ask you to do is, for example, how much force does it take to maintain this right where it is? Well, you have a lot of forces going on here. So like, for example, if this is 100 kilograms, that means you have a force straight down, and that force is your magnitude of that force, and that's 100 kilograms. Now, some other forces you have a force that's pushing it down. Okay, this is actually referred to as F parallel. Now, to pull it up, that would be negative F parallel. Okay, which means then you have, if things are parallel, And then that would mean that you have F parallel down here. And then you have another force pushing on the ramp. So just think of yourself standing on a 2x4. If you stand on a 2x4 like this, you're going to bend that 2x4. Same thing if you stand on a 2x4, whoops, that didn't work. Sideways, you're still going to put a bend in it even if it's on an incline. Well, this is F parallel. Now in physics, they're going to go through a lot of different ways of doing this. And if you have taken physics, they'll say, for example, that this is angle maybe 30 degrees. Some will say that this is 60, so you can use either angle. And you find that most of the time you're always looking for this or the acceleration of the object if it's going down or up. But let me give you a different approach here. So if this is your x-axis at 30-degree angle, well, that means these are components of root 3 over 2 and 1/2. Which means that if you just multiply your magnitude by those, so if you go 100 by your components, root 3 over 2 and 1/2, you have now components of 50 root 3 and 50, which means that this is your F perpendicular and this is your F parallel. And you have your information from that right off the bat. Now, like I said, sometimes, if I'm teaching a trig class, and we haven't done components, obviously, one of the things I do is I say 30 degrees, I say the sine of 30 degrees is equal to F, but I don't call it parallel because I haven't talked about it yet. But that would be my F parallel over 100. So I set it up that way, and you get the same thing, F parallel equals 50. Okay. So anyway, something to think about in physics when you see that incline thing, a little bit faster way of maybe finding the solutions than some other ones. Also, too, keep in mind that sometimes you look at example that this is kilograms. You might see them do this at 9.8 meters per second squared, because that way when you multiply all this out, you have 50 times 9.8, and that would be then a Newton. So when you look at solutions, sometimes it might be given to you as a Newton, so you wonder why they threw on gravity. That's why. Okay. Now, let's look in terms of the acceleration of the object going up or down. Well, that would be Newton's second law. So if you look at, let's say, F equals ma, that would mean your acceleration then is F over m. And your force is your net solution. So your net solution would be your mass times gravity, which we just did up here, sine of theta, over your mass. Now, what is this? Well, that's your unit vector right there. Anytime you say sine of theta, that would be a unit vector of that piece. Also notice your masses cancel out. So basically, all you have is gravity. So your gravity sine of theta. So here's your unit vector. And gravity would be 9.8 of 1/2, since it's 30 degrees, our ramp. And therefore you have 4.9 meters per second squared. It's your acceleration at an incline at 30 degrees if the object started going down. Okay. One last thing just to add on to this. So let's do the same thing here. Here we have my 50 kilograms. But let's do this. Let's put a pulley here. And I'm going to pull it up or down. Actually, yeah, I'll be pulling up with 60 kilograms. So obviously it's going to accelerate up this direction. So this would be considered my mass 1, and this is my mass 2. So again, we use Newton's second law of F equals ma, A being your net force over your mass. Well, what's my net force? Well, you have m2 here. That's your mass 2 times gravity, and you're going to take away your other one, which is mass 1 gravity sine of theta. So notice this is the same thing we just did, but you have to divide it by mass 1 plus mass 2. Well, I don't know if this looks familiar, but remember this, when we were doing center of mass, SOM, center of mass, when we divide it by the total masses. So notice that comes back into play. So some way of remembering this is putting those pieces together. Okay? So if we looked at this and finish out the math part of it, you would have, and we can pull out the gravity here. I'm going to pull out G, so I just do it once. So I have 60 minus 50 times my unit vector, half, times my gravity, 9.8 meters per second squared. Notice these are kilograms in here. And my masses here would be 60 plus 50, and we have kilograms on the bottom. So notice my kilograms cancel out. And if you plug this in, you should get 7.5. And notice the only thing you have left is measurements of meters per second squared, and that would be an acceleration. So anyway, the only thing you'll have to learn on how to do this in physics would be when you have friction involved, and that's going to be with your college physics teacher. So anyway, just want to throw out some ways of remembering some of this stuff.